Wait a minute, that doesn't sound right. How did happy birthday turn all depressing? In this video, we'll be talking about the physics of harmony, the physics of what essentially allows us to take a happy song and turn it into a depressing one. Stay tuned. Sound exists as longitudinal waves, but we can also depict them as transverse waves, allowing us to explain wave interference much more easily. Wave interference is a phenomenon that occurs when two waves meet while traveling along the same medium. They merge into one wave, which takes the form that results from the net effect of the two initial waves. If we add up two perfectly synced waves together, the crests of the waves would sum up, as well as the troughs, resulting in a wave that now has higher crests and lower troughs. However, if we displace the second wave along the axis of time, then the crests of the first wave will meet the troughs of the second wave, and vice versa. This would result in the two waves completely cancelling each other out. When two waves interfere, the amplitude of the resulting wave at a given point is equal to the algebraic sum of the two amplitudes of the two waves at the same location. This is known as a principle of superposition. Now let's talk about music. In music, notes are divided into octaves, which are essentially groups of 12 notes. Keep in mind that octaves are repeating. In musical terms, we call the third note of every and any octave D, and so forth. Thus, when defining a specific note, we specify the name of the note as well as the octave it is in. Each note has its own specific frequency. If we have two notes of different frequencies played together at the same time, then wave interference causes certain parts of the two sound waves to cancel out or add up. For example, if we play the note A from the 4th octave, which has a frequency of 440 Hz, and the note E from the 5th octave, which has a frequency of close to 660 Hz, the resultant wave looks like this. Different frequencies with specific ratios is what produces harmonics. In music, names are given to all of the ratios that exist. These ratios are completely dependent on how far the notes are away from each other, not what the notes actually are themselves. This is because the frequency of notes increases exponentially, not linearly. For example, 660 Hz to 440 Hz forms a ratio of 3 to 2, commonly known as a perfect fifth. If we shift both of the notes up by 3 semitones, the ratio still holds. Musicality is thus dependent on relative pitches, not absolute frequencies. It turns out that the simpler these frequency ratios are, the more consonant or pleasant the notes sound. In contrast, notes with more complex frequency ratios produce more dissonant harmonies. Dissonance typically causes tension and desire to be resolved, so melodies tend to move from dissonant harmonies into more consonant ones. Even music, something perceived to be so subjective, can be explained through math and science, and that's what math and science are ultimately about. Understanding how the world around us works.